Definitely concentrate with them. So one of the things we talked about was the single replacement reaction, and one of the single replacement reactions that we used as an example was a reaction of copper with silver nitrate. And we said that this was a little bit difficult for us to understand off the top of our heads because the copper forms a copper 2 type compound. So it was copper nitrate like this, and then silver. And of course, we wouldn't leave it unbalanced. We would balance this. So what are you suggesting? Put a 2 here. Okay.
Over there by the, is that working for me? Can't see, I'm sorry.
I'll need some more silver.
That's silver.
This is single replacement. And how do we know it's single replacement? Let's review. How do we know if it is direct combination? One product. There's one product. How do we know if it's decomposition? One reactant. How do we know if it's single replacement? An element and a compound that reacts together to make an element and a compound. So that's what we have here. An element and a compound, they react together, waka waka waka, and they're making a compound and an element. I have this reaction. Here's a piece of copper. What I've done is it's actually 3 little strands of copper that I've braided, so there are little holes in between. And the reason for the holes is because as this reaction takes place, the silver is going to plate out onto the copper because it happens, the chemistry happens where they come in contact with each other. This is a test tube that's got a little bit of silver nitrate in the bottom. Now I'm going to put the wire in here, and you'll see that the wire doesn't fit entirely into the solution, and that's a good thing. Because if you keep it upright as we pass it around, then the top part should stay nice and silvery copper looking, and the bottom part will actually show you the silver that's plating out. Now it starts to happen right away. As soon as I put it in there, the bottom part of the copper will sort of gray up, and that's the silver that's being plated out. The people in the front row won't get to see it real well, but they can see it a little bit. But by the time it comes back around again, there'll be chunks of silver hanging off of the copper. And since copper 2, you might remember this from your lab experience, is a blue solution, the solution here should turn blue as more and more of the copper dissolves and replaces the silver. So you can take it and pass it down the line. You can see the silver already plating out, and those little openings between the braiding will fill up with silver as we pass it along. Now, one of the special reactions that takes place in single replacement is the reaction of a very active metal, something like sodium, with water, H2O. Now, for most chemical purposes, I think this would be to your advantage to think this way. For most chemical purposes, it will be to your advantage to think of water not as H2O, but instead to think of water as HOH. Because when water reacts, and this is particularly true next semester in Chemistry 12 and Chemistry 1152, the reactions that take place are much easier to understand if you think of water as HOH. So it's not hydrogens and oxide, but rather it's a hydrogen and hydroxide. Now, if this is a single replacement reaction, what element will the sodium be replacing? One of the hydrogens, in fact, the hydrogen. And it's going to leave the hydroxide intact. And so if it replaces the hydrogen, it pairs up with the hydroxide. And so what would the correct formula be? Remember, your first job is to write correct chemical formulas. What would the correct formula be for sodium hydroxide? It's NaOH. And then what element is left alone here? A hydrogen, but we write it as
H2.
H2 because it's a Hunkelbrief. So we're always in our mind testing, is this a Hunkelbrief? Should I write it as 2? and with hydrogen we do. Now, is this balanced?
No.
So,
2, 2, 2.
so, and we're good. Now, this reaction is very energetic. The end of this chapter, hopefully today, maybe not, we're going to talk a little bit about the energy of chemical reactions, and this particular reaction is very energetic. Did I blow off a pop bottle in here?
No.
Okay, the H2 and the AO2, and blew out a little flame going on. Okay, that's a very energetic type of reaction as well. But this reaction is very strongly energetic, gives off a lot of heat, and the hydrogen that's produced mixes with oxygen in the air. And hydrogen and oxygen can react, as you saw in the pop bottle, to make water, if it has some kind of heat trigger. Well, this reaction produces enough heat to actually ignite the hydrogen that's given off. Yes, ma'am? Doesn't ring a bell. There is nothing that has one product and one reactant. Oh, well, in the types of reactions, okay, so direct combination was one product. Decomposition was one reactant. Single replacement was compound and an element. So I actually have a video. One of the things that you'll be doing fairly soon as the semester comes to an end here is you'll get a message from the associate provost telling you that the evaluations are ready for you to do. You get to evaluate the course and you get to evaluate the instructor. And one of the things I always take a hit on every semester is technology. I don't use PowerPoints, I'm not a big computer guy, but today I brought my computer and I'm showing you a video. So when you get that evaluation, you'll be able to
Maybe.
rate me high if I can find. Oh,
Magic's good, magic's good.
I'm looking for Google here somewhere. Oh, it's under stuff.
I don't just type it in.
Just
Search engine. There we go. There we go.
It'd have been faster. Potato.
Okay, so ignore the little setback there and just remember that this is an awesome video that he brought his computer for you to actually watch. Okay, this is a government agency back in 1947 who had a little bit of sodium left over from the war effort. Somewhere in the neighborhood of 20 to 30,000 pounds of sodium. And they didn't know what to do with it.
You said a little bit.
Yeah, it's a little bit.
Okay.
And so they didn't know what to do with it, so they decided to get rid of it. And so here is how they got rid of it.
$30,000 pounds of highly dangerous metallic sodium head for destruction in Lake Lenore, Washington. The government surplus chemical ignites and explodes when wet. The alkali lake is devoid of fish and forms an admirable disposal spot. A 3,500-pound container of sodium hurtles into the lake and crashes through a foot of ice. As the water seeps in, smoke rises through a series of muffled explosions. The acrid clouds billow several thousand feet over the steep sides of the lake. Disposal of the chemical by the War Assist Administration is made necessary because no public carrier will accept it for transportation to a purchaser. One after another, with varying effects, the containers go up with spectacular results as water and sodium meet. A once lethal war chemical becomes a peacetime pyrotechnic display.
And the smoke wasn't.
Yeah, I don't think we could get rid of that today in the same fashion. But it's a pretty impressive little video. I think. So remember evaluation score. Interesting video. So it fits right in with single replacement reactions. Look at the form. An element and a compound. We're kicking something out, replacing it, and we get a compound and an element. So a single replacement reaction.
I have a question.
Yeah.
So how do we know that the sodium bonds with the hydroxide and not the hydrogen?
That's an excellent question. If sodium is going to be in a compound, what charge would it have? +1, right?
Yeah.
And so, what's your guess? Is sodium going to pair up with the positive hydrogen or the negative hydroxide?
Negative.
Because there are no gay chemical compounds, right? Not that there's anything wrong with that, but in chemistry, we pair up the positives with the negatives, and we get our result. So it's a good question, but we have a good answer for it as well. All right, other questions? Another similar type of reaction is one where we're using an active metal and an acid rather than just water. So iron, for example, will react with hydrochloric acid. Now again, here we have a difficulty that when we're dealing with a transition metal, which iron does it form? Unless we have some evidence, we don't know. So we have to be told it's going to form the iron 2 compound. The iron 2 compound. So can you write a product and balance the reaction for this reaction if you're given the information that it's single replacement and it forms an iron 2 compound? Go. You have 12 seconds to make this happen. Oh, you missed the coolest video. But, no, they'll tell you how to rate me at the end of this in the area of technology. That shouldn't be there.
Oh, I know. I was just for that to
Yeah,
figure
number
out
you want
the
over it.
thing. Dr. Braun.
Ma'am.
If it's 2, then do I need 2 of these?
Yes, you will.
And do I put a 2? No?
Why would you?
Okay. Is that what you want?
Okay, so the answer should be the iron is going to pair up with the what? The chlorine. And the chlorine is a -1. The iron, I told you, is
Sprinkle hot.
+2, so it's got to be FeCl2. And then the hydrogen that's left over is
We
a
have 2
Hankel group, so
chlorines
it's
and 2
H2.
hydrogens on this
And
side.
are we balanced?
No.
What would we do?
2 HCl.
Okay. We're going to come back to single replacement reactions with a little bit more evidence for them in a second. But meanwhile, we're going to go on to the 4th type of chemical reaction.
Your hair's down. Oh.
Going on to double replacement. Okay, we've done direct combination. How do you know? One product. Decomposition, one reactant. Single replacement, compound and an element. Double replacement, the dummy reaction looks like this. So it's 2 compounds. Okay, 2 compounds. So double replacement, again, the name makes a great deal of sense. Double replacement, what are we doing? We're replacing 2 things, right? This is an easy one to remember. It's the kinky reaction, because what are the compounds doing? They're switching partners. Okay? So the A is going to pair up with the D, so I'm going to get AD and CB. Why CB? Because we always put the positive first in our compounds, right? And we know that C is the positive because it occurs first here, and B must be the negative from here. So we're keeping track of positive and negatives. Yes, sir. You're okay? All right. So let's take a look at this reaction. There's also a problem that occurs with this. So let's do sodium chloride and potassium nitrate. Okay. I should be having you name these things. What's the name of this?
Sodium chloride, potassium nitrate.
I knew I got the best class. Okay, so what we're going to do here is to switch the partners. Now remember, your job remains the same. What's your first job? Correct chemical formulas. So we follow the pattern and we say, all right, we're switching partners. So the sodium is going to pair up with the nitrate, the positive with the negative. So what's the charge on a sodium? Don't look at the board. What's the charge on a sodium?
Positive 1.
What's the charge on a nitrate?
-1.
A little weakness there, which means what? Get them flashcards out, because these are polyatomic ions, and if we're losing our polyatomic ions, we can't afford to do that. We're still using them. Just because that test is over doesn't mean you can do a memory dump on everything that we had, right? We use this stuff as we go along. So it's a -1, sodium's a +1, correct formula.
Na, open parentheses. And then,
Well, we don't need a parentheses because there's just one
okay.
of the nitrates, but it would look like this. Okay, then what's the other combination?
KCl.
Okay, KCl. You got it already. Good. KCl. And so there is a double replacement. It's obvious that it's happened. They've switched the partners. Now, in truth, here's the kicker to this. Nothing has happened.
What?
I'll tell you why. What happens when we put salt in water? All of you are familiar with salt, and you know what happens when you put salt into water.
Ocean.
You get salt water, okay? What does the salt do?
Dissolve.
It dissolves. It actually does more than that. It doesn't only dissolve, but it breaks apart. It's what we call dissociates or ionizes into a sodium ion and a chloride ion that exist separately in the salt solution. The potassium nitrate does the same thing. So since I'm doing this in water, that's the only way to get these things really to react with each other. I actually have sodium ions and chloride ions and potassium ions and nitrate ions, like so. Now, I've let the double replacement reaction happen, and I end up with these two products over here, which are also salts, which are also soluble in water, and which also dissociate into water. So what do I actually have here? I have the sodium ion, and the nitrate ion, and the potassium ion, and the chloride ion. Now remember, somebody asked this question last time, does it matter how you order them on one side of the arrow or the other side of the arrow? And the answer is no. It doesn't matter how you write them, except that you got them on the correct side of the arrow. You have a reactant as a reactant and a product as a product. So look, is there any difference between this side and this side?
No.
There isn't. And so even though on paper this looks like a pretty good double replacement reaction, in practice nothing has happened. Now I brought that with me today. Here is some sodium chloride dissolved in water, and you can see that it looks like water, okay? Because that's what it looks like when it's dissolved. This is potassium nitrate dissolved in water, and it looks like water because it's dissolved. So what I'm going to do is to actually place some of the potassium nitrate into some of the sodium chloride. I'll take a dropper full and squirt it in. Voila! Look!
Wow.
Nothing has happened, right? Because all I've done was mix some ions together. There's been no effective chemistry taking place. Well, does that mean that there's no such thing as a double replacement reaction? The answer is no. we can have effective double replacement reactions. Suppose we took sodium chloride and silver nitrate. Let's do the double replacement first. Can you get me the products? I'll let you try it.
So, what if this was on the test, would it be put, it was just not effective?
Let's not go there yet.
Well, I just wanna know what it is.
I'm going to summarize for you.
You're gonna summarize?
Yeah.
'Cause I'm confused.
Silver chlorine, chloride. Remember we changed the MD. So we should end up with NaNO3 and AgCl, right? Now let's go back and do our little analysis like before. Sodium chloride. Well, you already know that that dissolves and dissociates into water. So that's actually the sodium ion and the chloride ion. Silver nitrate, soluble salt, goes into water, dissolves, dissociates. So I get silver ion and nitrate ion. Other side, sodium nitrate. We already had that guy. Dissolves and dissociates into sodium ions and nitrate ions. Silver chloride, here's the difference. Silver chloride is a solid. And if a solid forms, then there's been some real chemistry that took place. Well, let's see that one. All right. I have another tube of sodium chloride, ordinary table salt in water, and I have a bottle of silver nitrate. So I'm going to take and add some of the silver nitrate to the test tube of sodium chloride. And let's see if we get a reaction that takes place. Voila. We get now no Alka-Seltzer, because Alka-Seltzer would have an effervescence, a gas given off. This doesn't. But it's definitely a solid formation. And I'll pass this around and you can see it, that the solid is slowly drifting down. Eventually it'll all accumulate at the bottom. But it's separating itself from the rest of the solution, so there's been an effective double replacement reaction that takes place here. So we have ineffective double replacement reactions, we have effective double replacement reactions. What if it was a test question? Let's say that for the test purposes, we will assume that our double replacement reactions are effective. And if you're asked to do one, then you do one. Okay, sometimes I'll give you the information, oh, silver chloride is a solid, so you're comfortable with the fact that something happens. Or barium sulfate is a solid, or whatever the solid may be that is produced. Another effective reaction is one that produces a gas. Because what would a gas do if we had an effervescence in our reaction? It escapes from the solution and again separates itself. As long as it's separating, then some real chemistry has taken place. So double replacement reactions, as far as we're concerned, will be effective. That's an S. For solid.
And you'll tell us if it's a solid.
Or you just assume that it works. Okay? We're not going to pull any of this tricky stuff that says, oh, this doesn't really work. Sorry, you balanced for nothing.
Dr. Braun,
I'm not going to do
I have a
that.
question.
Yeah.
When the sodium was placed in the ocean earlier in the video, and then there was an explosion, why does that not occur if sodium and chlorine dissociates? Sodium chloride dissociates in water.
An excellent question. An excellent question. The sodium that goes into the lake is this. It's sodium metal, so it exists in the atomic form, and as an atom, it's very unstable because it does not have the electron configuration of a noble gas. So the reason sodium is as reactive as it is as a metal is because it's trying to become like that noble gas electron configuration. When you dissolve salt in water, you're not getting sodium metal, you're getting the sodium ion.
Okay.
And the sodium ion is something that has already lost its electron, noble gas configuration, and it's quite content to be what it is. So there's no explosion that should take place.
This is kind of silly, but if sodium chloride disassociates in water, why does salt water taste salty?
Because you're getting both ions to interact with your taste buds.
Okay, so it is.
Okay, in fact, even if you put solid salt on your tongue, that's not what you're tasting. You're tasting the stuff that the saliva is dissolving and dissociating into the ions, and the ions are probably the ones doing the interacting with the taste buds. I'm sorry?
We're actually tasting the reaction.
Yes. You're tasting an interaction. Whether it be a reaction or not depends on the biology, and I don't go there. So. But yeah, there's some kind of, our receptors, taste budding has to be a chemical reaction of some kind. There has to be some reaction that occurs that ends up sending a signal to the brain that, ooh, this tastes salty. Okay, and we have receptors, taste buds, that do that for salty substances. And so whatever that reaction is, and I don't know what that reaction is, but it would be probably, my guess is with the ions, not with the actual solid material. It's pretty rare for solids to react with each other, although I have one example for you if we get to it today. Okay, in this type of reaction, we still see some things that don't look like they participate at all. In other words, look at the sodium. You've got a sodium ion on one side, a sodium ion on another side. Chemical reactions, like mathematical equations, if you have the same thing on both sides of the equal sign, or in this case an arrow, they can actually be canceled. So we could get rid of that sodium, like so. We can get rid of the nitrate, like so, because they're the same. And what we're left with is actually Cl minus plus Ag plus, giving us AgCl as a solid. Now that's what's called the net ionic equation. That's showing us the actual guts of the chemical reaction. This is what's happening. The other guys that we've canceled out are called spectator ions. They're just there watching. They are truly spectators. They're there along for the ride. Now, caution, we couldn't do it without them. Because how are you going to get chloride to react independently with silver unless you have some source of chloride? But chloride doesn't come alone. You can't go into the lab and find a bottle of chloride ions on the shelf. Nature demands electrical neutrality, which means you've got to have a positive and negative balance. So we've got to, if we want chloride, we've got to take something that has paired up with the chloride, and in that case, sodium chloride works quite well. And so it's necessary, but it's what we call a spectator. If we're looking at just the hardcore chemistry that's taking place, we would look for the net ionic equation rather than the entire equation.
One more time. But the cancel out and the one in blue is the net ionic equation.
Net ionic.
Ion. Okay. It says, what about the cancel out?
They're spectators.
Spectator.
They're what we call spectator ions. They're just watching what's going on.
Why didn't you cancel out the Ag?
I can't, because this is not Ag+.
Oh, okay.
If it were an Ag+, I could do that, but I can't, because it's in a different chemical environment. It's no longer Ag+, it's now bonded in a solid AgCl. And so that leaves me with the net resultant ionic equation down here with the AgCl as a solid.
So that's a question like that when I taste the lab departments should be tolerance.
I don't know. It depends on what the way the question's worded. Probably what I'm going to do is give you what are called the molecular equations. These are called the molecular equations. They include the entire molecule. They don't just isolate the single ion that's doing the actual work, but they show you the entire molecule that's there. And so we'll probably most often see the molecular equation and be asked to complete and or balance the molecular equations. So I doubt you're going to have to worry with ionic equations, but you may run across them and you'll want to see them for what they are.
Can you just like explain why I don't understand what you
Why I can't what?
cancel them out?
Cancel who out?
the spectator ion.
I did. That's what the blue lines do.
Yeah, why?
Why?
Why? Yeah, why?
Well, if a sodium ion is here and a sodium ion is here, has it done anything chemically?
No.
Then why include it?
Okay.
If it hasn't done anything chemically, it's not of interest to me at this point, I'm going to get rid of it.
Okay.
I'm going to recognize it as a spectator, but I'm going to eliminate it, so I'm going to cancel it. The nitrates have done nothing. They started as nitrate, they ended as nitrate, not of interest to me, I'm going to cancel them out. So that I can get to the point, I can get some tunnel vision here and see what is really taking place. And what's really taking place is this. Now again, I caution you, I can't get this to take place without these guys.
Right.
They're important, but they're spectators, and so for conceptual purposes, I can cancel them.
So can you do the kinetics?
Sure. All right, give this one a shot. First of all, how do we know the type? Two compounds. Two compounds tells me it's double replacement. What am I doing in double replacement?
Switching the positive and negative.
Switching the partners. So do that, get me two products, because two compounds should give me two compounds. And then we'll see if it's effective or not.
Is that B, A, or B, E?
I have BA. Like people call it barium.
Oh, okay.
Can be. Well, depends what form of the barium. We'll talk about that. Well, if you drink this form, you're dead. Yeah. But if you drink the product form, you survive.
You're so bad.
Very coffee. I was telling someone else they do.
Oh, yeah, they do. And now it's flavors.
Is this how I'm supposed to be the one who's switching the positives with the negatives?
You are violating the first rule.
I put my positives with my negatives.
Y'all put a 3 in front of me.
Are you balancing?
That's a positive.
I'm not
Well, how do you know if you end up putting a 2 here, wouldn't there be 6 of them?
No,
Should you balance before you complete the,
no.
what's your first job?
Write the correct,
Chemical formulas, you've got 1.
So do I write it just as it is? Do I just put this up for it?
Here's the killer. You write a correct chemical formula.
Oh, just put
No, I'm
the,
saying, do
I
I leave
need
it
the
as it
charges.
is? Yeah.
You write a correct chemical formula.
My question is, do I write it as it is on this side?
Is this correct?
No, it's not.
Then you don't write it. You write a correct chemical formula. You have to go through the combination. What's a barium? What's a sulfate? How do they combine together? What's the formula? You have to write a correct chemical formula. You don't look at what you have already.
AL3CO2.
So let that influence.
okay, Dr. Braun, question. So I need these charges. That's what you're saying by it's not the correct. So like this is +2.
Right.
This is +5.
Oh, is it?
So you get BASO4 for your first.
What is it? 3? And it needs to be.
SO4.
Okay, I guess time is up.
Okay.
Let's see what we get. We should get Not yet.
I'm
Wrong.
gonna fail my test.
Let's
But I knew that was right.
get to the point where I really see it. Okay, so if this is our first job, writing correct chemical formulas, and how did I get this? Barium is a, what charge?
Plus
+2. Sulfate is a
-2.
-2. Correct combination would be 1 to 1. BaSO4. Aluminum is a +3. Chloride -1. Correct formula AlCl3. Now I can balance.
Okay, I get it now.
Or is it balanced?
it is not balanced. You got 2,
Want 2 here?
no,
No. Nothing there? Want a 2 there?
put a 3 in front of the BA
Put a 3 where?
in front of barium.
Here?
Yeah, and then put a 2 in front of AL.
Exactly. I don't know what's going on.
Okay, how many people are confused?
Yeah, wait.
All right, well, let's go back and start over. Let's balance it together. I'll just start with the barium. I got 1 barium here and
1.
1 barium here. I got 2 chlorines,
3.
3 chlorines. So I need more on this side. I'm gonna put a 2 here. It's mine. It's my problem. Now I've got 4 chlorines and 3 chlorines. Where do I need more? The only thing I can do is put a 2 here. Oh crap, now I've got 6 chlorines, so I'll put a 3 here. And if I put a 3 there, then the BA needs 3. And then I've got 2 aluminums, and now I've got
2
2
aluminum.
aluminums. I've got 3 sulfates and
3.
3 sulfates, and so I think now I'm balanced.
Yeah.
Yes, sir.
Could you explain before you do the P and B, how you got the 3 on chloride and you drop the 3 on?
Sure. Who's combining with who here? Positive what? I mean, tell me the element. What element's combining with what element? Good enough. Stop. What's the charge on a BA?
Oh, we're not done.
Done?
Wait out.
All right.
We have to cancel.
And what's the charge on a sulfate? It's not on that paper. It's up here, dude. Flashcards. Help them out. Minus?
2.
-2. Okay. How did I know that? I memorized it. I worked with my flashcards. And I know sulfate is -2. I know this is +2 from the periodic table. It's positioned in the periodic table. Now, this is +2, this is -2. What ratio will they combine in to give me a neutral compound? 1 to 1. So it's BaSO4. All right? Who else combines?
Chloride.
All right? What's the charge on a chlorine?
It's minus 1.
It's -1. Look where it is with respect to the noble gases. And what does it have to do to become like a noble gas? It gains 1 electron. Electrons are negative, so it's a -1. What's the charge on aluminum?
3.
Plus 3. So if this is a -1 and this is a plus 3, in what ratio will I combine them to get a neutral chemical compound?
3 chloride.
And that is my first job. So what happens is if you don't know your charges on polyatomics or whatever, you're screwed on the first step. Okay? But they tell me it's easier the second time. Yes, ma'am.
I was confused about earlier about the chlorine on the shelf and not realized how.
Yeah.
Either a combination reaction separated the sodium and chlorine to make the
Right.
CO2.
This chlorine I can find on the shelf.
But not just-
This chloride I cannot find alone. The chloride has to have a positive mate. The chlorine is already neutral, and I can get that in a bottle by itself. So these are different chemicals. Just like we talked about these being very different chemicals, these are very different chemicals as well. Okay? All right, so we've got the balanced molecular double replacement reaction. Now, can I break this down into ionic form? Yeah, I could. Okay. What would the barium chloride break up into? The barium ion, which is +2,
Ba plus 2.
and the chloride ion, which is
Cl minus.
Cl minus, and the aluminum ion, which is,
Al plus 3.
and the sulfates,
SO4 minus 2.
and they will give me, now here's the tricky bit, this guy's a solid. So this gives me barium sulfate, as is. Aluminum chloride is not a solid, so it's the aluminum ion.
Al plus 2. Cl minus. Oh, plus 3. Plus 3.
Now in truth, I could go back and put in the coefficients for all these guys, because how many bariums will this balanced molecular form give me? 3. How many chlorides?
3.
6.
Oh yeah, you have to
Because
multiply.
there's 2 in the package and I've got 3 packages of them. How many aluminums? 2. How many sulfates? How many barium sulfates? How many aluminums? How many chlorines?
6.
Okay. And now if I wanted to, I could go back and cancel the spectators. Are they obvious to you? And so the net ionic equation is that 3 barium ions plus 3 sulfate ions give me 3 barium sulfates. Now, in truth, all those coefficients are 3. I could reduce them to 1 and 1 and 1 if I wanted to.
How do you want us to write that out?
Just like this.
Just 3 BA?
Yeah.
3 SO4?
Well, Ba plus 2,
That's what I'm saying, can you write how you?
like this. So what you just said was 3Ba. I dispute that.
We have
It's
to write.
3Ba plus 2. If you don't have that plus 2 on there, it's a different chemical. Just like we've been talking about with the sodium and the sodium ion. These are different chemicals, very different chemicals. You cannot confuse them, so you cannot just drop the charges and have it mean the same thing.
So it's gotta be 3 BA2 plus 3 SO4 minus 2. Arrow, 3 BA SO4.
Yes.
Okay.
And if you want to put a little S there for solid, that'd be fine.
But you told us that.
I did tell you that. And in this case, if you wanted to reduce all the 3s to 1s,
You could,
that would be fine as well.
but I should leave it like that.
You could. Yes, ma'am.
The cancellation process where we get the net ionic equations, can that only occur with double replacement?
Probably.
Okay.
It's the only thing that comes to mind. Now, barium chloride is a soluble salt, and it gives us this barium ion. The barium ion is extremely toxic to humans. You want to kill somebody? Barium ion is a good element of choice. Okay? Now, don't make me appear in a courtroom testifying that I told you in class that this would actually kill somebody. Okay? But it will. The barium ion is a heavy metal ion, and heavy metal ions in general are effective poisons. A lot of insecticides use heavy metal ions as their poison ingredient. However, when you react it with sulfate, you make this barium sulfate solid. This is what we give to people who need a GI series X-ray, because the barium is a heavy metal, which means it's going to block X-rays very effectively. So we give them a barium milkshake, as it's called. It's actually barium sulfate, and they drink it. Why does it not kill them?
Because it's sulfate?
Because it's a solid, and it is not available as the ion. It is a very insoluble salt. If it were barium chloride that they mixed up, you'd be dead. It's barium sulfate. It's solid, stays as a solid, goes through the system, is treated like roughage, and is expelled from the body with no damage to us. And in the meantime, we can take an X-ray, and it blocks the X-rays, so it outlines the gastrointestinal tract, so it can be seen for problems or whatever.
Do it again.
What, poison somebody?
Oh.
I don't think you're not very good.
Well, that's scary.
Another problem.
Oh, another problem. All right.
No, you're being turbo.
You don't. Now, years ago, in a different textbook, we had an appendix page that allowed you to coordinatedly map the positive and negative guy in a column in a row, and where they met, it gave a symbol that told you whether it was a solid or not. Our textbook doesn't have that, so we don't have that capability. So that's why I say, as far as we're concerned, double replacement reactions will happen, okay? Or I will tell you when they're solid or not solid.
Transition.
Okay, time is up. You should get zinc chromate, ZnCrO4, 1-to-1 combination, because zinc is +2, chromate -2, and sodium chloride, NaCl. And so we need 2 of those to balance the reaction. Good?
So Dr. Vaughn, the solid is on the chromate and oxygen only, not the zinc.
No, it's on the zinc chromate.
Zinc
Remember,
chromate.
that's 1 unit.
Okay.
And we write it like that, it's 1 unit.
Okay.
Okay? Moving on.
No, don't go anymore.
I need to work on the number first. Okay.
Ready?
Okay.
Okay. One of the problems we have in chemistry is that I can't teach you everything in one day. It'd be great if I could, but I can't. Consequently, we sometimes find ourselves ahead of ourselves. We want to talk about one thing that fits in with chemical reactions, but it involves something that we haven't talked about yet. And what I'm talking about are some substances called acids and bases. We haven't really defined them or talked about them or described them to you yet, and we won't until like chapter 9, I think it is, 8 or 9. So if I want to do a chemical reaction with them right now, I've got to give you some little bit of background into what they are. So I'm going to give you the cheap version. I'm going to give you the quick and dirty definition of an acid. For our purposes today, the definition of an acid is a chemical compound whose positive guy is hydrogen. A chemical compound whose positive guy is hydrogen. Therefore, HCl. Look, there's a chemical compound and the positive guy is hydrogen. So this is an acid. Okay? H2SO4 would be an acid because it's a compound and the positive guy is a hydrogen. HNO3 is an acid. Compound, positive guy, a hydrogen. So this works for us for the time being. Now, definition of a base. A chemical base is a chemical compound whose negative guy is hydroxide. A chemical base is a compound whose negative guy is hydroxide. So, NaOH would be a compound whose negative guy is hydroxide, should be a chemical base. KOH, compound whose negative guy is hydroxide. And how about CaOH2, compound, negative guy is hydroxide.
His negative guy is an oxide.
Hydroxide. Hydroxide is OH minus. Okay, so a type of double replacement reaction that gets special treatment is a double replacement reaction called neutralization. Now, realize it is just a double replacement reaction. It's a special one. It is the double replacement reaction that takes place between an acid and a base. So is it correct to call it double replacement? Yes. Is it correct to call it neutralization? Yes. Would we call the ones we did on the upper board neutralizations? No, because they're not acids and bases, but they are double replacements. So all neutralizations are double replacements, but not all double replacements are neutralizations.
Say that one more time.
Yes.
All neutrals.
All neutralizations are double replacements, but not all double replacements are neutralizations. Yes, ma'am.
So when those type of double replacements, all of them would have to be an acid again, or then
No, if it's going to be a neutralization, we're going to have one acid, one base. Okay? If there's a metal in there, And we're probably talking single replacement, because we'd have a compound and an element.
I'm lost. Repeat again.
About what?
That all element replacements are neutralization.
All double replacements are not neutralizations. All neutralizations are double replacements.
That makes no sense.
Okay, so you said all neutralization is one acid and one base, right?
Yeah.
Okay, can you give an example of it?
I'm going to give 3 examples.
Okay, cool.
The 3 that are on the board.
Wait, one more question. Is that another type of reaction, neutralization, or is it just what it is?
It is a special type of double replacement.
Just a special type of.
Yeah. Yeah. So, I think you'll like these, because look carefully, what will always be one of the products?
HOH.
Water. You're going to have the hydrogen from the acid pair up with the hydroxide from the base, and when you get hydrogen and hydroxide to pair up, you make water. So in every one of these cases, water is one of the products.
Is that for all neutralization?
Yes. I'll say yes. Yeah. And the other product is what we call a salt. Now, you're used to salt being NaCl. That's table salt. That's what you put on your French fries. But in chemistry, there are hundreds of salts. And these neutralization reactions all make a salt. Let's look at the first one. In this case, the hydrogen pairs up with the hydroxide. Now, what's the charge on a hydrogen? +1. Charge on a hydroxide?
Minus.
So the combination is 1 to 1. I would write it as HOH. Remember, that's going to be an easier way to view water. It's going to help in the balancing if you do that. You can write it as H2O. That's correct. There's nothing wrong with it. But I think HOH is a little bit better conceptual form. All right. Then what other combination do we get here? Sodium with chlorine. What's the charge on sodium?
+1.
+1. Chlorine.
-1.
Correct formula.
NaCl.
NaCl. So notice that we once again have done our first job correctly. We have written correct chemical formulas.
You have to, does it have to be NaCl first?
Doesn't matter which side, what order those come in, as long as they're on the correct side of the arrow.
Okay.
So, are we balanced?
Yeah.
If we're not, what are we missing? And look how the balancing will go. We're going to treat hydrogens different than hydroxides. So how many hydrogens on the left? 1. How many on the right? 1. How many hydroxides on the left? 1. How many on the right? 1. How many sodiums on the left?
1.
On the right?
1.
Chlorines on the left?
1.
On the right?
1.
We're balanced. Let's try the second one. Notice it's double replacement, 2 compounds, and more specifically, it's an acid with a base. So, what are some of the pairings? Hydrogen's going to pair up with hydroxide. Do not look at the board. You're looking at the board. Do not look at the board. What's the charge on a hydrogen? Charge on a hydroxide. Correct combination. HOH. That's what you have to do. Because I'm telling you, most of you are going to look at this and write H2OH. And the red pen will fly. Okay? It is incorrect. It's HOH. Remember, our first job is to write correct chemical formulas. Our second job is to balance. So we don't want to balance at the same time we're writing the formulas. All right, who's the other pair?
Okay.
Potassium with sulfate. Don't look at the board. What's the charge on potassium?
+1.
+1. Sulfate. -2. Correct combination.
K2SO4.
There we go. K2SO4.
Salt.
We have done our first job successfully. We have written correct chemical formula. What's our second job?
Balance.
Is a balance.
No.
Oh, what do we do?
2 in front of
Two.
KOH, 2 in front of HOH.
Let's do it?
Yeah.
We're bad. Yes.
Is there a reason why we were writing the HOHs on the
No. Work. I'll do the next one differently. How's that? Just to mix things up. Okay. If we get water in the next one. All right. What's our next guy? Double replacement. How do you know? Compound plus compound. Neutralization. How do you know? Positive guy's a hydrogen. Negative guy's a hydroxide. Who are the combos? Hydrogen with hydroxide. Don't look at the board. What's the charge on a hydrogen? Charge on a hydroxide. Correct formula. HOH. That's right. All right. Other combination. Calcium and nitrate. Don't look at the board. Charge on a calcium.
+2.
Plus 2. Charge on a nitrate.
-1. -1.
Oh, dang. Yeah, just a minus.
How did you know that?
Memorize.
Because you memorize them from your flashcards, right? Good girl. Others are not so good. So, if it's a +2 for calcium and a -1 for nitrate, what's the correct combination?
CaNO2.
CaNA3,2.
I don't know what you said.
C8.
This?
Yeah.
Okay. Notice we've done our first job, which is
Right.
write correct chemical formulas. Second job.
Balance the
Are we balanced?
No.
Maybe we are.
No. Put a 2 in front of the HNO3 and a 2 in front of the HOH.
We're good?
Yeah.
Logical?
Yeah, sort of.
Making sense? Clicking? And solo? All right, go. 12 seconds.
No concept what's going on.
Well, then we need to talk. Yeah, we need to come out.
Why'd you need two?
Because I wanted to see if you were paying attention. That's why. Good class. Trouble?
Two.
And of course, these get better with
Practice.
Practice.
Type of reaction.
Single.
Single replacement. Who's got the little tube with the copper in it? Sit around. All right, notice, especially those of you in the front, look at the difference. You can actually see the blue. I'll hold it away from my shirt. And you can see the bottom has tons of flocked silver on the copper wire where the single replacement reaction has occurred. So we got it to take place. We got this single replacement reaction happen. Now, let me pose this question to you. What type of reaction is that?
Single replacement.
Single replacement, because it's an element and a compound. But here, there's no reaction. Makes sense. If I take this tube now and say, okay, let me pass this around again, will it unreact because it's going through the class a second time? No. There are chemical reactions that tend to happen in one direction. And so when you try to make them happen in the other direction, they say, no, we won't go. So the big question before us is, how do we know? When do I know when it's going to happen or when it doesn't happen? We have had a great set of chemists before us to blaze the trail and to do the investigation. And what they have done is through countless experiments, they have found what's called the activity of certain substances. And the activities give us a clue as to what happens in single replacement reactions. So, let me get this off while things warm up. We have what's called the activity series. Now, I don't think your book does this, but there's a copy of it on the website if you want to get it, and you don't have to memorize it. It's something that we'll give you when we need to use it on an exam, or we'll give you a short version, or we'll give you information from it, or whatever. So, what we have is a on switch. Well, the title up there says activity series. You can see it on top of the board. Here is the activity series. It's a list of commonly used elements in single replacement reactions, and it rates them by this thing, this property called activity. Now, here's what we're going to do to use this. Any element that is above another element in the table is said to be more active. So, zinc is more active than iron. Aluminum is more active than zinc. Okay? The more active guy wants to be part of the compound. That's the thing to remember. The more active guy wants to be part of the compound. So, when I have copper plus silver nitrate, all right, who are the two metals in competition? Silver and copper. Find them in the activity series. Who's more active? Who wants to be part of the compound?
More
Who
active.
is part of the compound currently?
Silver.
So reaction will take place. And the copper will kick the silver out and form the copper nitrate and kick the silver out to be alone.
Can you
Yes.
go over that again?
Yes. The guy that's higher in the activity series is more active than anything below it. The more active guy wants to be part of the compound. So, copper and silver, where are they in the activity series?
Copper is above silver.
Who's more active?
Copper.
Who wants to be part of the compound?
Copper.
Who is part of the compound?
Silver.
So it's going to happen. He's going to kick him out.
Oh, okay.
So, and if it was the other way around, like
Let's try it.
CuNO3 2Ag, you couldn't make a compound.
Okay, who are the metals in competition?
Ag and Ca.
Find them. Who's more active?
Copper,
Who wants to be part of the compound?
copper.
Who is part of the compound? Nothing's going to happen.
Okay.
No reaction is going to take place.
Why is hydrogen bolded?
Hydrogen is bolded because he's not really a metal, but he plays a very important role here because hydrogen is the positive guy of what types of substances?
Acid.
Acids, right? So what this does is this tells us what metals will react with an acid or not. For example, if I have zinc plus HCl, what type of reaction is this? Single replacement. Okay, it's a metal, it's an element and a compound. Who are the two guys in competition? Zinc and the hydrogen. Who's more active?
Zinc.
Who wants to be part of the compound?
Zinc.
Who is part of the compound?
Hydrogen.
He's going to kick him out. And so what's he going to do? He's going to react with this and form zinc
Chloride.
chloride. Zinc is a
Plus 2.
+2, chlorine,
Minus.
correct formula?
CO2.
Plus H2.
Do you remember the second lab we did in the lab? The empirical formula of zinc chloride? We put a piece of zinc in a little porcelain dish and added hydrochloric acid, and it bubbled away. Gave off hydrogen gas, formed zinc chloride. What if I take a piece of copper with HCl? Who are the two competitors? Copper and hydrogen. Who's more active? Who wants to be part of the compound? Who is part of the compound? Nothing happens.
No reaction.
Copper will not react with hydrochloric acid. All right, we'll pick up on this again on, thank you, Thursday.